Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is kind of the last one of a review of functions for trig and college algebra. And so it is assumed that you've seen functions, obviously, but this is usually the last topic you see with functions in an Algebra 2 course. And because of that, I assume that this is kind of shaky ground for most students. So we're going to spend a little bit of time really developing the concepts here. This will be broken into several different lectures. So the first thing we're going to talk about with inverse functions is just verifying that two functions are inverses of each other. We're not really going to start with what is an inverse or what is a one-to-one function. We're actually just going to kind of take a 30,000 foot view here. So we know that functions have the property that each input leads to a single output. That's a critical part, so I'm going to highlight that. And now that's the defining characteristic of a function, right? Each input just goes to a single output. So it's this picture right here. X, you plug into the function, and something happens on the inside of this we just don't know, and it all of a sudden pops out an output that we call Y. And it won't pop out two different outputs, so there's no possibility for it to pop out Y and Y2 or something like that. That won't happen, because if that happened, it would not be a function. Now, we're going to investigate exceptional functions which have the additional property that each output leads back to a single input. A lot of students initially see this and say, well, isn't that what all functions do? But that's not true. Remember that if I had a function that mapped from this domain here to the range over there, what I can do, let's say I have inputs A, B, and C. Let's just make our lives easy and just say those are the inputs. We don't need a whole laundry list of them, just a few of them. And let's say the outputs here are, I don't care, lowercase a, lowercase b, lowercase c. It doesn't really matter, right? A function means that you have an input A that gets mapped to one of the outputs, an input B that gets mapped to one of the outputs, and an input C that gets mapped to just one of the outputs. And notice that is a function. The input of capital A does not map to two different items. But not only is that picture a function, so is this one. Capital B maps to lowercase b, and capital C also maps to lowercase b. That is still a function, right? Because each input just leads to a single output. The input of capital C leads to a single output B. The input of capital B leads to a single output, well, just happens to be B. But this is not the special function we're talking about here. The exceptional function where every output leads back to a single input, because the output of B here actually maps back to both capital B and capital C. So this is not that exceptional function that I'm talking about. We want to know what makes those functions so exceptional that the outputs map back to single inputs. So not only do these inputs map to single outputs, but vice versa. And this brings us to our very special definition of these very exceptional functions. A function f with a domain D is called one-to-one if no two elements of D have the same image. Now, let me just tell you, that's a very, very rigorous definition, actually. And what that really means is that each input of the function f leads to a single output, and each output leads back to a single input. And that's kind of what I've written here. This is the same thing as saying that f is one-to-one if each input leads to a unique output, not shared by any other input. I probably wouldn't even say it that way, even though I did write that. So there's I think the better way of visualizing this is that each input leads to one output and each output leads back to one input. So often when you're introduced to this topic, you're introduced via tables and pictures and graphs, all these other things. And I already did a picture, actually. That was the very first page where I did the mapping from domain to range, that type of thing. However, we're going to go ahead and start traditionally with a table. We'll give you a function here, and we'll say make a table. So I'll make a table of x versus f of x. Let me zoom in here. X versus y, which is equal to f of x. And so our inputs, well, we can plug in anything we want. I'm just going to go ahead and make my table go from -2 all the way to +2 in step sizes of 1. It's just a little bit cleaner to have that that symmetry, I guess. If you were to plug in -2 to the function, you get -8 minus 4 or -12. If you plug in -1, you get -1 minus 4, which is -5. If you plug in 0, you get 0 minus 4, which is a -4. And finally, or not finally, but if you plug in 1, 1 minus 4, -3. And 2, that'd be 8 minus 4, which is 4. All right. So, made a table of values. Does it appear to be one to one? In other words, does each input lead to a single output, which is silly. It totally does. Each input does lead to a single output. That's why I called it f of x, because it is a function. But the real question is, does each output seem to lead back to a single input? And just from this very small list, the output of -12, that only leads back to -2. The output of -5, well, that only leads back to -1, and so on and so forth down the line. So just with this small list, sure, it appears to be one-to-one. Notice I put emphasis on the word appears. It's not that I'm telling you this is not one-to-one. I'm just saying we can't really guarantee it's one-to-one because we only took a finite number of sample points. It could be that some point later on there's a y value that is born from two different x values. That's very hard to do with to see with a table, and that's why I dislike table questions, is because they're very misleading. You could really just happen to select values that don't showcase the true function's behavior. And so because of that, I find that table problems are pretty bad. And now we get to actually the main focus of this section, which is inverse functions. Now, a lot of students really know about inverse functions, but they forget about the phrasing one-to-one function. A one-to-one function is the official word, or the official phrasing for a function where each input leads to a single output and each output leads back to a single input. That type of function is called a one-to-one function. However, the mapping that goes backwards from y back to x, that is called the inverse function for the one-to-one function f. So that's what this definition is saying, is let f be a one-to-one function. Then the inverse function, which should have been bolded, honestly, right there, is denoted with this terrible notation and is defined by the following. I'll talk about that notation in a moment, but I'll say it this way. If you know that f of x is equal to y, then it is the case that we will use the notation f inverse of y is equal to x. That's if the function f is one-to-one. Now I want to talk about a few things here, notationally, because this does become critical as you move through mathematics. So a little bit of notation. That notation right there, which is, you've seen me write the implication sign before. The implication sign looks like this. And usually that means, let's say I have something here and something there. It means if P is true, then Q must be true. That's what that notation means. But this notation right here, it's called a bijection. You don't need to know that name. It's just its official name. And we could talk about it the same way. It means that if P is true, then Q must also be true. And if Q is true, then P must be true. In other words, the arrow points both ways. One implies the other, so P implies Q and Q implies P. This is a very powerful style of statement, a bijection is, and that's what we search for in most of our arguments in and outside of mathematics. And by the way, the language for that is if and only if. That's if you hear somebody say this is true if and only if the other thing is true, that means if the first thing is true, then the second is true, and vice versa. If the second thing is true, then the first thing is true. Whereas this notation right here, which is how most theorems are written, honestly, only says if P is true, then Q is true. It does not say if Q is true, then P is true. A great example for this, very famous one, is when somebody says, if it's raining, then it must be cloudy. Right? That's this statement right here. So if it's raining, then it must be cloudy. That statement does not go the other direction. If it's cloudy, then it must be raining. No, that's not true. That's not true at all. It could be cloudy without rain, but if it's raining, there has to be clouds. Okay? So that's what an injection is. And you don't need to know that word, by the way. All right, so I'm going to zoom out here. And again, we have a one-to-one function. Then the inverse of that function is denoted with this notation right here, and is defined by that notation of y is equal to x if and only if f of x is equal to y. Now that notation is called the inverse function notation. And I want to focus in on that a little bit. So let me write that down here. F inverse of, you saw it in the theorem, or I guess definition, that it's f inverse of y, but a lot of people will write it f inverse of x, but I'm sticking with y for now. You'll see it'll switch to x in a while. But that notation is not 1 over f of y. It's very, very, it's a very unfortunate notation, period. It's a terrible notation. However, it's the notation that's been used for quite some time, and we can't get away from it for some stupid reason. So you're just going to have to suck it up and understand that whenever you see f with that picture, which I'll never call an exponent, then it means it's f inverse, or the inverse of f. It's not 1 over. Again, that's a huge warning, and I sincerely hope you don't make the mistake, because it's very sad when it happens. So let's bring into our nomenclature that word inverse. So consider this function, g of x is equal to the cubed root of x plus 4. Does it appear to be the inverse of the function f from example 3.7, number 1? Let me just recall that example. Here it is right here. And you can see that we have our table already pre-built, ready to go. So let me go ahead and just copy that and paste that over. And I should also write out what f was, right? F was x cubed. I think it was minus 4. Let me just double check. Yes, that's exactly what it was. X cubed minus 4. All right. So let's go ahead and see if f and g are inverses of each other. So let's build a table for g. Now remember, we're only checking to see if it looks or appears that g undoes f, or g is the inverse function for f. So we're going to plug in values into g and see what their outputs are. Now the values I'm going to plug in, because I want to see if g is the inverse of f, well, I'm going to take the outputs of f and I'm going to plug them as inputs into g to see what happens. So that output of negative 12, and we have an output of negative 5, and we have an output of negative 4, and an output of negative 3, and finally an output of positive 4. Let's see, with each of those outputs for the function f, what happens when we plug those outputs into the function g. So looking at g, if I let x equal negative 12, add 4, that's a negative 8. The cubed root of negative 8 is a negative 2. If I plug in -5, I get -5 plus 4, which is a -1, and the cube root of -1 is a -1. If I plug in -4, add 4, that's 0. Cube root of 0 is 0. Plug in -3 and add 4, you get 1. Cube root of 1 is 1. And plug in 4, you get 4 plus 4, or 8. Cube root of 8 is 2. Notice I had originally an input of -2, it led to -12, and so on and so forth down the line. And now I have the output of -12, and it leads back to the input, leads to -2, which looks like G is taking the outputs of F and returning back to the inputs, the corresponding inputs. Well, let's just double check that with everything. So I'm going to look through, I'll pre-highlight. I'll look at -5, -4, -3, and +4. And notice where they lead. They lead to -1, 0, 1, and 2, which are identically what they were coming from in our original case with the function f. So it appears that g is the inverse of the function f from example 3.7, number 1. And it's critical to remember why I'm saying that. Because if you take a look at this, the function f takes as its input some value of x, it returns as its output some value of y. The inverse function will take that output y and turn it back into x. Oops, that was supposed to be blue, so let me do that properly. What I call, there are a lot of inverse functions you could possibly think of in life, but one of probably the most popular inverse functions is parents and children, as far as cleaning goes. A parent will clean up after their kids. Their kids will undo that operation and make it a mess again. And a parent will undo their children's operation by cleaning it up. And then children will make it a mess again. They undo each other's actions. They are inverse functions of each other, not the parent and the child, but those specific actions. That's a good way to kind of think about it. I like the idea of a machine too. The machine diagram that is very popular in mathematics is this diagram right here, where you have some function f, you plug an x into that function, you don't know what happens on the inside. So we call that a black box operation. You have no clue what happens on the inside. It could be cubed and subtracting 5 or something like that. You just don't know. But out pops a value of y. What the inverse function will do, it's another machine that will take as its input that output, that value of y. Again, there's some type of manipulation done here on the inside. We don't know. And then out pops the original value of x. So for example, if you had a machine that tied shoes and another machine that untied shoes, you would plug a shoe into the machine that ties shoes and out pops a tied shoe. And then you plug that tied shoe into the undoing machine and out pops an untied shoe. You're back to the beginning. There are a lot of different ways you can kind of visualize this, but I kind of figured those two methods or those two ideas are pretty solid. So that being said, you can see why I say it does appear that f and g are inverse functions, because with the function f, you plugged a -2 into it. Well, that's not the machine diagram, but anyway, you plug a -2 into f here, and out pops -12. However, if you plug that -12 into the function g, it takes that input of -12, and you can see it pops out -2, which is exactly what you started with. So g seems to be undoing whatever f is doing. And so we arrive at this theorem, which basically codifies exactly what we've been saying. If f is a one-to-one function and f inverse is, well, it's inverse, then I'm going to say this in language so you really can start thinking of functions this way. If I take an input and plug it into the inverse machine, it'll transform that input into some value. Let's just pretend it transforms that into the value y. F will undo that. It'll take that y and transform it back into x. And so they undo each other that way. Same thing for the second statement here. If you take an input and plug it into our function f, well, that'll return some output we'll call a y value. The inverse function will take that y value and return you back to the original starting point, which is x. Notice the notation. It's very sad notation, to be honest with you. The input for f inverse, naturally, we think of that as the output of the function f. But just letting you know that we will often let x stand for the input of either f inverse or f itself. So it will get a little bit confusing, but as time goes on, you'll hopefully see why. Another notation for these compositions is that fog notation you've seen in Algebra 2, I think, where f composed with f inverse of x and f inverse composed with f of x. I don't use that notation because I think the actual nesting notation, the function notation's a little bit better. And the proof of this, well, I always find that it's important, especially in college, that you see proofs and you start to feel comfortable with them. So let's go ahead and talk about the structure of a proof. With a proof, you can always assume the if part. Somebody comes in the room, they say, if this is true, then that is true. Well, they're saying you can assume the first part, the if part, is true. You have to show the that part, the then part is true. So I can assume the if part. So I will just assume that right now. Let me zoom in. And notice the notation I'm using here. It's very common just to shorthand the words one-to-one with 1-1. That's all. The next thing you're going to do in any proof is rely upon definitions and theorems. And being able to assume that f is 1-to-1 and f inverse is its inverse, we can say the following just from the definition. In fact, I'll hop back and show the definition. We're going to steal that notation. We're going to say, well then, f of x is equal to y is true if and only if f inverse of y is equal to x. And that's just from the definition. So we're not really cheating or anything like that. We're just using the definition. It's like somebody saying, suppose we have a chair. Well, if we've defined what a chair is, then I can say, well, then it's an object that I can sit on or whatever it is, however you want to define it. Okay, so let's see what we want to arrive at. We want to investigate what is f of f inverse of x. Let's go ahead and do that. Let me zoom in here. Hence, f of f inverse of x. Well, if we assume that f inverse of x is equal to some value, and unfortunately, I don't want to use y here because I just don't want to. So I'm going to say, let's suppose that f inverse of x is equal to k, assuming. Well, then if I assume that f inverse of x is equal to k by the actual definition that we have, this definition right here, if f inverse of x, you have to pay attention to the lettering here. That's an x right now, and that's a k right now. If f inverse of x is equal to k, then by definition, f of k is equal to x. Again, I'll just showcase my change in lettering. It's just because of the way we decided to do this. So this implies that the f of k is equal to x, thus f of f inverse of x, which is equal to f of k. Well, since f of k is equal to x, that's equal to x. And so we have proven that f of f inverse of x is equal to x. And really the unfortunate part is the notation in that theorem, but it actually will work fine for the second part. So let's go ahead and now suppose that y is equal to f of x. Well, by definition, f inverse of y must therefore equal x. So I just set that up as my pre-argument. Now I'm going to go ahead and look at where I want to arrive in the second piece. I want to look at f inverse of f of x. And I want to arrive at x. So let's take a look at f inverse. And I'll put this implies that f inverse of f of x is equal to, well, we've just said if y is equal, that we're assuming y is equal to f of x. That's the letter we're going to use for that, or the variable, I should say. So this is just the same thing as f inverse of y, but by definition, f inverse of y is just the same thing as x. So we've now just shown that f inverse of f of x is equal to x. And the proof is done. QED, or quod erat demonstratum. So it has been demonstrated. This is a very short proof and kind of almost a little too easy, because you end up, I'm not saying it's easy for you to do. What I'm saying is it's a little too simple, and generally very simple proofs end up throwing people off because it seems like it's way too obvious. And so a lot of people just say, well, it's true because it's true. It's not true because it's true. It's true because it's been proven to be true. So let's go ahead and take a look at a very last example before we pause in this video process here. So if I give you two functions and you want to test whether the functions are inverses of one another, this is how it's done. You're just going to determine whether f of g of x is equal to x or g of f of x is equal to x. If either statement is true, then both are true. So if you find out that f of g of x turns out to be x, then f and g are inverses. And by the way, g would be f inverse, and likewise f would be g inverse. If either of the statements is false, then both are false. In other words, if you find out that g of f of x is not x, then g and f are not inverses. So really what it comes down to is play with compositions. If you want to determine if those two functions right there in example number 3, if they're inverses, well, just look at f of g of x. This is kind of why you start playing with inverses in mathematics, so that you can check whether or not functions are inverses to each other. That's not the only reason. There are a ton of other reasons, but that's the initial. And that's f of, instead of g of x, I'll just write out what g of x actually is. That's the cubed root of x plus 4. Notice how I'm doing this. I'm following the order of operations. I'm just looking at the innermost function here, which is x. I can't do anything there. And then I hop out and say, well, what's g of x? And I write that. And then I look at this stuff and I say, I can't simplify that, so let me hop outside of that. What's f of that picture? Well, f of a picture is the cube of that picture minus 4. That's what f is defined to be. The cube of a picture minus 4. What is the picture? That thing right there that we're plugging in. It's the cube root of x plus 4. The cube root of a picture raised to the third power, well, we all know that's just going to be x plus 4 to the first, and then minus 4. The 4's cancel, and you get x. So thus, that means that f composed with g of x is equal to x, which implies f and g are inverses, which also implies that f, let me finish this out, which also implies that f is equal to g inverse and g is equal to f inverse. They're just inverses of each other. They undo each other. All right, so that's how you check to see whether functions are actually inverses of each other, and included in that was a review of inverse functions. Critical topic, going to be essential as you move into the trigonometry part of a trig and college algebra course.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.